A dead star, the size of Earth, but weighing as much as the Sun. We thought we knew what happened inside one. We were wrong. Inside a white dwarf, crystals are floating upward through liquid plasma, pumping out heat and stopping the star from aging. Some of these objects are billions of years older than we ever calculated. Tonight, we go inside them. We watch stars eat planets. We witness the explosion that outshines entire galaxies. And we find out what these dying stars say about the death of the universe itself. If this sounds like something you want to experience, hit like and subscribe. We start now. A star dies. What it leaves behind breaks every rule you thought you knew. Picture our sun, a burning sphere so massive that 1 million Earths could fit inside it. Now strip away all the fire, all the gas, all the fury. What remains is a white dwarf, a dead core the size of our entire planet, packed with almost everything the sun ever was. That is where we start. When a medium-sized star like our sun burns through its hydrogen fuel, it does not go quietly. It swells into a red giant first, ballooning outward until it swallows the inner planets whole. The outer layers puff away into space, forming glowing shells of gas called planetary nebulae. Beautiful, colourful, gone. What stays behind is the core. No more fuel, no more fire, just a ball of carbon and oxygen sitting in space, slowly losing heat. Scientists call it a stellar remnant, a corpse, a white dwarf. But here is the thing about this corpse. It is one of the most extreme objects in the known universe. The moment that core is exposed, with nothing pushing back from nuclear fusion, gravity crushes the material inward with violent force. The original star, which was roughly the size of the sun, collapses down to a sphere, roughly 7,900 miles across. That is about the width of Earth. You could drive across one pole to pole in about a day if roads existed in space. Now hold that thought. The entire mass of a star, almost as much as our sun, compressed into a ball the size of our planet. Let that image build in your mind before we go further. The density is unlike anything you have ever touched. A single teaspoon of material from its core weighs roughly 11,000 pounds. That is heavier than a pickup truck, heavier than 2 full-grown elephants. Pick up a teaspoon from your kitchen right now and imagine it holding that weight. Your arm would not just bend, the floor would crack. And that is just the teaspoon. The gravity on the surface is 100,000 times stronger than what you feel standing on Earth right now. If you somehow stood on a white dwarf's surface without being instantly crushed, you would weigh something close to 15 million pounds. Every bone in your body would flatten in a fraction of a second. There is something stranger coming, though. Something about what keeps this object alive. Because despite being dead, despite having no fusion engine, despite cooling slowly into space, the white dwarf does not collapse. It holds its shape. It resists the crushing gravity forever. And the reason why is not chemistry. It is quantum mechanics. A rule so deep in the fabric of reality that even gravity cannot override it. We are going to get there. But first you need to understand just how thin the skin of this object really is. The atmosphere of a white dwarf, the layer of gas sitting on its surface, is less than 150 feet deep. Stand inside a sports stadium, look up. That is roughly the height of the atmosphere on a white dwarf. On Earth, our atmosphere stretches 60 miles above our heads. On this object, it barely clears the roof. Every heavy atom in that razor-thin layer sinks almost instantly, pulled down by gravity so strong it sorts the atmosphere like a perfect filter. What floats on top is almost always pure hydrogen. The surface below that thin layer is where things get genuinely strange. Temperature here starts above 180,000 degrees Fahrenheit when the star first forms. Over billions of years, it cools, slowly, very slowly. But scientists in 2024 discovered that the cooling is not steady at all. Something inside is fighting back. And it changes everything we thought we knew about the age of the universe. 5 billion years from now, our sun will kill us. It will do it slowly, almost gently, and when it is done, what remains will be a white dwarf floating in silence where our entire solar system used to be. This is not distant mythology. It is physics, and the process has already begun in stars older than ours all across the galaxy. Right now, the sun burns hydrogen at its core. That fusion reaction releases outward pressure. That pressure pushes back against the sun's own gravity. The two forces balance. The sun stays stable, has stayed stable for about 4.5 billion years. But hydrogen runs out. When the core hydrogen is gone, the sun cannot maintain that balance. Gravity starts winning. The core contracts and heats up. That heat ignites a shell of hydrogen surrounding the core, and the extra energy pushes the outer layers outward. The sun begins to expand. Over hundreds of millions of years, it swells into a red giant. It grows so large, its surface could reach close to where Earth currently orbits. Mercury vanishes first. Venus follows. Earth gets scorched or swallowed entirely, depending on exactly how far the expansion reaches. Oceans boil away. The atmosphere strips off. The surface bakes at temperatures that melt rock. Nothing survives. But the sun keeps going. In the red giant phase, it starts fusing helium in the core once helium has accumulated. The star pulses and shudders. Its outer layers get agitated. Then, over tens of thousands of years, those outer layers drift away in waves. They float outward into space, forming a shell of glowing gas lit up by the dying star at the center. We would see that shell from another star system, a glowing ring in the sky, beautiful. And sitting at the center, exposed and alone, is the core, our sun's core, a white dwarf, roughly the size of Earth, made mostly of carbon and oxygen, the ash left behind from billions of years of nuclear burning. It has no fuel left. No engine. It just sits there, radiating heat into space, beginning a cooling process that takes longer than the current age of the universe. And here is the part that most people do not think about. All the planets that survive far enough out, Jupiter, Saturn, Uranus, Neptune, they keep orbiting this dead star. The solar system does not disappear. It reorganizes around a cold, slowly fading core. Mars, if it survives the red giant phase, might still orbit a white dwarf sun billions of years from now. The gravity does not vanish just because the fire does. The white dwarf holds the remaining system together, but it also does something violent. The intense gravity of that dead core begins pulling on any object that drifts too close. Asteroids get tugged. Comets get redirected. Remaining debris from the inner solar system spirals inward toward the new white dwarf. Some of it gets ripped apart, torn to shreds, sucked into a glowing ring of destroyed rock orbiting the dead star. Scientists have already watched this happen around other white dwarfs. They detected the chemical signatures of destroyed planets dissolved into the thin hydrogen atmosphere of dead stars across the galaxy. Rocky material, minerals, the remains of worlds. This is what our solar system will look like. A small, dense, fading core, a few frozen outer planets in distant orbits, and a field of debris, the wreckage of everything that used to exist closer to the sun, spiraling slowly inward. The universe moves on, quiet and cold. But the white dwarf has not finished surprising us yet. What is happening inside it right now, as it cools, is something nobody predicted until very recently. Pick up a spoon, hold it in your hand. Feel how light it is. Now imagine that same spoon scooping out a tiny amount of material from the core of a white dwarf. That spoonful would weigh roughly 11,000 pounds. You would not feel it getting heavy. You would simply be crushed the moment you touched it. This is the reality of white dwarf density, and understanding it changes how you see what matter actually is. On Earth, atoms have space between them. Even solid steel is mostly empty. The electrons orbiting each atom's nucleus stay at a comfortable distance. There is room, structure, air in the gaps. In a white dwarf, that space is gone. The collapse of the dying star compresses the material so completely that the electron clouds of neighboring atoms are forced into contact. Then, pushed further, the atoms get packed so tightly that they form a kind of plasma, a hot, dense soup of atomic nuclei floating in a sea of electrons that have been stripped free. Scientists call this state degenerate matter. The word degenerate here does not mean broken or damaged. It means that the normal rules of matter have been replaced by quantum rules. The electrons in this state do not behave like electrons in your kitchen table. They obey a different physics entirely, and the result is a material with properties that seem impossible. The density is roughly 1 million times greater than ordinary matter. If you took a beach ball made of white dwarf material, it would weigh more than every car ever built on Earth combined. The entire mass of our Sun, compressed into a sphere roughly the size of Earth, produces this kind of density throughout. Now compare that to something familiar. The Sun currently has an average density similar to water, not heavy water. The Sun is big enough that its gravity holds it together even at that relatively low density. A white dwarf is 1 million times denser. Same gravity source, 1 million times smaller space. Trying to dig into a white dwarf with anything we have ever built would be like trying to scratch a diamond with a cotton ball. The surface is solid beyond anything we have a word for. But here is where it gets stranger. Despite being this impossibly dense, the material inside is not actually frozen solid everywhere. The outer layers near the surface are solid, but deeper in, the carbon and oxygen exist as a pressurized liquid plasma, hot and churning, even while the star is technically cooling and dying. And inside that liquid, something is starting to grow. Crystals, tiny crystal structures of carbon and oxygen, forming slowly as the temperature drops. Scientists knew about this. They expected it. What they did not expect was what those crystals do once they form. They float. The crystals are slightly less dense than the liquid plasma around them. Just like an ice cube in a glass of water, they rise toward the surface instead of sinking. And that upward motion sets off a chain reaction that pumps energy back into the star, delaying its cooling by billions of years. We will get to that discovery. It rewrites the age of the universe. But first, you need to understand the force that made this density possible. The force that should have crushed the white dwarf all the way into a black hole, and why it stopped. The answer is one of the strangest rules in physics. Stand on top of the Empire State Building. Look out. You are about 1,400 feet above street level. Now look straight up. Our atmosphere stretches roughly 60 miles above your head. 60 miles of air, weather, wind, and oxygen, keeping every living thing alive. Now imagine all of that compressed into a layer less than 150 feet deep. That is the atmosphere of a white dwarf, less than the height of a 15-story building. So thin you could walk from the bottom to the top of it in under a minute. So thin that even calling it an atmosphere feels generous. This is not a flaw. It is what happens when gravity becomes 100,000 times stronger than what holds our own air in place. On Earth, our atmosphere stays because gravity is just strong enough to hold gas molecules from floating off into space. Lighter gases like helium do slowly leak away at the top over geological time, but the bulk stays put for billions of years. On a white dwarf, gravity is so extreme that it pulls every gas molecule down with terrifying force. Any gas that tries to rise gets slammed back down almost immediately. The result is an atmosphere that has been physically squeezed into a paper-thin shell sitting on the surface. And this gravity does something else remarkable. It sorts the atmosphere perfectly by weight. Every element has a different atomic mass. Hydrogen is the lightest. Helium is next. Then carbon, oxygen, iron, silicon, calcium, and so on up the scale. On Earth, these elements mix together in the atmosphere. The turbulence of wind and weather keeps everything churned. On a white dwarf, There is no wind powerful enough to fight the gravity, so each element sinks to the level exactly matched to its weight. The heavier ones drop almost instantly. They fall through the thin atmosphere and get absorbed into the denser material below. What floats on top is almost always pure hydrogen, or, in some white dwarfs, pure helium. Nothing else survives at the surface. The gravity filters it out in what astronomers estimate is a matter of days to years, which is nearly instant on cosmic timescales. This makes white dwarfs fascinating crime scenes. When astronomers detect something other than hydrogen or helium in a white dwarf atmosphere, they know the star has recently eaten something: a planet, an asteroid, a comet. The heavy elements from that destroyed object pollute the atmosphere temporarily before gravity pulls them down and buries them. Scientists have found calcium, silicon, iron, and magnesium in white dwarf atmospheres this way. These are the same minerals that make up rocky planets, the same stuff as Earth's crust. So when we find those signatures sitting above a white dwarf, we are looking at the dissolved remains of a world. Something drifted too close. Gravity tore it apart. The debris rained down. And for a brief window, the chemistry of a dead planet floats in a layer thinner than the building you might be sitting near right now. The atmosphere burns at temperatures that drop over billions of years. Early on, the surface sits above 180,000 degrees Fahrenheit. Ultraviolet light pours off in waves, surrounding gas clouds left over from the original star's death glow in greens and blues lit by that radiation. As the star cools, the ultraviolet fades, the glow dims, the atmosphere narrows further, but deep beneath that razor-thin shell, something is still happening, something that keeps the interior far hotter than it should be for a star this old. The crystals are rising. Gravity has one job: pull everything inward. Compress, crush, never stop. In most cases it wins. Gas clouds collapse into stars. Stars eventually collapse into neutron stars or black holes. Gravity does not give up. But in a white dwarf, something stops it cold. And that something is not heat, not pressure, not any force we experience in daily life. It is a rule written into the fabric of quantum mechanics, one of the deepest laws governing how matter behaves at the smallest possible scale. It is called the Pauli exclusion principle. Here is what that means in plain terms. No two electrons can occupy the exact same quantum state at the same time. Think of quantum states like seats on a bus. Every seat can hold exactly one passenger. Once a seat is filled, no one else can sit there, no matter how hard you push. In a normal gas or liquid, electrons have plenty of room, plenty of empty seats. Gravity compresses the material, but there is always somewhere for the electrons to go. In a white dwarf, gravity has squeezed the material so far that all the low-energy seats are filled. Every available state is occupied. There is nowhere left for the electrons to move when gravity tries to compress the star further. The electrons physically cannot get any closer together, so they push back. Scientists call this electron degeneracy pressure. It is a quantum force, not a thermal one. Regular gas pressure depends on temperature. Heat the gas up, pressure rises. Cool it down, pressure falls. But degeneracy pressure does not care about temperature. It holds cold or hot as long as the electrons are packed tightly enough. This is the reason a white dwarf does not need to keep burning fuel to survive. It does not need to generate heat to hold itself up. The quantum rule does that job permanently. And the effect is unlike anything else in the universe. The white dwarf is essentially frozen in place by physics itself. Gravity pulls inward, quantum mechanics pushes back. Neither wins. The star holds that size and density essentially forever. Forever is a long word. But in this case, it applies. Without some outside force adding mass to the white dwarf, electron degeneracy pressure holds the structure stable for longer than the current age of the universe. But here is the part that should feel genuinely unsettling. This protection has a limit. Add enough mass to a white dwarf, and the electrons get squeezed into states with higher and higher energy. They push back harder, but at a precise point, the pressure cannot keep up with the incoming gravity. The system breaks, and when it breaks, it does not break slowly. The collapse happens in less than a second, and what follows is one of the most violent events the universe produces. We will get there. First, though, understand what the Pauli exclusion principle means for everything we think we know about matter. In your body right now, the reason your hand does not pass through this screen is ultimately electron degeneracy pressure. The electrons in the atoms of your skin and the atoms of the surface repel each other because they cannot share the same quantum state. The same force holding your hand together is the same force holding a dead star together. It is just operating at a scale 1,000,000 times more extreme, and even at that scale it can break. Everything you have ever held in your hands follows one rule: add more mass, and it gets bigger. Fill a balloon, add water to a tank, stack bricks on a pile. More stuff means more space taken up. White dwarfs work in reverse. Add mass to a white dwarf, and it shrinks. The more you pile on, the smaller and denser it becomes. It is one of the most counterintuitive facts in all of astrophysics, and it comes directly from the quantum mechanics holding the star together. Here is how it works. When extra mass lands on a white dwarf, gravity gets stronger. It pushes inward with more force. To balance that increased gravity, the electron degeneracy pressure has to rise. And for degeneracy pressure to increase, the electrons have to be packed tighter and move into higher energy states. Packing electrons tighter means the star physically contracts, less volume, more density, smaller size. This is the opposite of what happens in ordinary objects. It is backwards, and it holds true across the entire range of white dwarf masses. Picture two white dwarfs sitting side by side. One has half the mass of our Sun, the other has close to the maximum allowed mass, about 1 4/10 times the mass of our Sun. The lighter one is roughly the size of Earth. The heavier one is noticeably smaller, about the size of Mars, and enormously more dense. Keep adding mass to that heavier one, and it keeps shrinking. The electrons get squeezed into faster and faster states. At a certain point, those electrons are moving so fast, they approach a significant fraction of the speed of light. Physics at those speeds changes. The quantum pressure does not scale up as efficiently. And that is where the limit appears. At roughly 1 4/10 solar masses, the degeneracy pressure can no longer scale fast enough to beat the incoming gravity. The math just stops working in the star's favor. The result is a catastrophic collapse. Scientists have confirmed this behavior across dozens of observed white dwarfs of different masses. The pattern holds every time. Heavier always means smaller. The relationship between mass and radius in white dwarfs is precisely inverted from anything we see in normal matter. This inversion has real consequences for how we understand space. When astronomers observe a white dwarf and measure its brightness carefully, they can calculate how dense it is. From density, they can estimate its mass. From mass, they can predict its size. And that chain of calculations, from brightness to physical size, helps astronomers figure out how far away it is. White dwarfs have become measuring tools because their physics is so precisely governed by quantum mechanics. Their behavior is predictable in a way that most stars are not. But that precise predictability broke recently, because when scientists looked more carefully at the ages predicted by these measurements, they realized that something inside was generating extra heat. Something was adding energy the old models had never accounted for. The white dwarfs were lying about their age, and the thing making them lie is rising through their cores right now. There is a number in astrophysics that once crossed triggers total destruction. 1 4/10 times the mass of our Sun. That is the limit. Cross it, and a white dwarf does not slowly collapse. It detonates. In under a second, with enough energy to outshine an entire galaxy. The man who calculated this limit was a 20-year-old graduate student named Subramanian Chandrasekhar. He worked it out in 1930 during a boat trip from India to England, sitting on the deck, doing the math by hand. He was so young that the scientific establishment initially rejected his result. Too radical, too dramatic, too impossible. He was right. Today we call it the Chandrasekhar limit. It is one of the most important numbers in the universe. Here is what happens as a white dwarf approaches it. Every bit of mass added increases the gravity pulling inward. The electrons pack tighter. They move faster, approach the speed of light. At that point, the quantum pressure loses efficiency. It is not that the pressure disappears, it is that it cannot grow fast enough to match the gravity increase. As the star inches toward the limit from below, the balance becomes more and more fragile. The margin between survival and collapse narrows. The electrons are already moving at a significant fraction of light speed. There is nowhere left to go. Cross the limit, and the balance snaps. Gravity wins completely. Inward collapse begins. The carbon and oxygen core, which had been sitting stable for potentially billions of years, suddenly gets compressed. Temperature spikes, and carbon fusion ignites. But this is not controlled fusion like what happens in a living star. This is runaway fusion. The entire core begins burning in a chain reaction that cannot stop itself. Every part of the star ignites simultaneously. There is no gradual expansion, no slow red giant phase. The star blows apart. The explosion is called a Type 1 supernova. The energy released in that single event is roughly equal to what our Sun will produce over its entire 10 billion year lifetime. All of it in seconds. The light is so intense that a single exploding white dwarf can outshine every star in its galaxy combined for weeks. Astronomers around the world study these explosions obsessively, not just because they are spectacular, because they are predictable. Every Type 1 supernova releases almost exactly the same amount of energy, because every one is triggered by the same mass limit, the same physics, the same threshold. This makes them standard candles, objects of known brightness that astronomers can use to measure distances across billions of light years. If you know how bright something actually is and you measure how bright it looks from Earth, you can calculate how far away it is. Type 1a supernovae are so reliable that astronomers used them to discover something staggering about the universe. In 1998, two independent research teams measured supernovae at extreme distances and found that distant galaxies were moving away faster than nearby ones. The universe was not just expanding, it was accelerating. That discovery earned a Nobel Prize in 2011. It led directly to the concept of dark energy, all of it traceable back to Chandrasekhar doing math on a boat at age 20. One number, one limit, one explosion that changed how we see the cosmos. And the story of how a white dwarf reaches that limit is stranger than anyone expected. Two stars, born together, orbiting each other for billions of years. One dies first. It collapses into a white dwarf. The other keeps burning. And slowly, invisibly, the dead one starts stealing from the living one. This kind of pair is called a binary system. About half of all stars in our galaxy exist in pairs or groups rather than alone. When one star in a close pair runs out of fuel before the other, the white dwarf that forms sits close enough to its still-burning partner to have a significant effect on it. Gravity is the tool. The white dwarf's intense gravitational pull reaches across the gap between them. If the living star grows into a red giant and its outer layers expand enough, they drift into the gravitational territory of the white dwarf. The dead star begins pulling that gas toward itself. The gas does not fall straight down, it spirals. It forms a flattened spinning disk called an accretion disk that wraps around the white dwarf before funneling inward. This disk can glow bright enough to see across hundreds of light years. As the gas piles onto the white dwarf's surface, it adds mass. Very slowly, year after year, century after century. the white dwarf gets heavier. And remember what happens when a white dwarf gets heavier. It shrinks. It gets denser. Its gravity pulls even harder, which makes it siphon gas even more aggressively from its partner. The process feeds itself. Sometimes the stolen gas accumulates on the surface and reaches a critical temperature. The hydrogen ignites. A thermonuclear explosion rips across the surface of the white dwarf. In a flash, astronomers observe this as a nova, a sudden bright burst from a star system that previously appeared dim. The white dwarf survives the nova. It blasts the gas away. Then it starts feeding again. Some systems go nova repeatedly. Same pair, same white dwarf, over and over, every few thousand or few tens of thousands of years. But if the gas is not blasted away efficiently, if the white dwarf retains more mass than it loses in each nova, something else builds. The total mass climbs. Slowly, across millions of years, the white dwarf creeps toward the Chandrasekhar limit. Astronomers calculate that in some systems, a white dwarf could theoretically reach that limit from feeding alone. No merger, no external collision, just slow, patient theft from a companion star that never saw it coming. The companion loses mass steadily, its outer layers get pulled away, its life gets shorter. And at the end of that process, if the white dwarf crosses the limit, there is no second warning. No warning at all. One moment, a binary star system sits in the dark, two objects orbiting quietly. The next moment, one of the most violent events in the known universe erupts, where the white dwarf used to be. We already know what that explosion looks like, but what scientists discovered recently is that the slow build-up before it, the feeding, the cooling, the crystal formation happening inside the white dwarf while it waits, is far stranger than anyone expected. It happens in less than 1 second. The white dwarf, possibly billions of years old, suddenly cannot hold itself together. Gravity wins. The core collapses inward at tens of thousands of miles per second. Carbon and oxygen compress. Temperature spikes past 1 billion degrees. Fusion ignites, and the star erases itself. A Type 1, a supernova, is not an explosion in the way you picture a bomb going off. It is the complete and total conversion of a stellar core into energy. The white dwarf does not crack or fragment or burn down. It detonates. Every piece of it, simultaneously. The energy released is almost impossible to picture. Imagine everything the sun will ever produce over its entire 10 billion year life. All of that, released in a few seconds, from an object the size of Earth. The shockwave expands outward at roughly 30,000 miles per second. If that shockwave passed through our solar system, it would cross the distance from the Sun to Earth in about 1.5 hours. An event that large, moving that fast, what remains is a rapidly expanding cloud of hot gas and newly forged heavy elements. Iron, nickel, silicon. Elements cooked in the brief but intense fusion burst. These elements get scattered across hundreds of light years, eventually seeding future star systems with the raw material for planets. The iron in your blood was forged in explosions like this, and for weeks after the detonation, the light from a single white dwarf explosion can outshine every star in its host galaxy combined. Every single star, outshone by one object. Galaxies contain hundreds of billions of stars. A Type 1, a supernova, visible from billions of light years away, briefly beats all of them together. Now here is what makes this scientifically crucial. Because every Type 1, a supernova, is triggered by the same mass limit, they all release almost exactly the same amount of energy. Astronomers know in advance how bright each explosion actually is. If you know the true brightness and measure the apparent brightness from Earth, you can calculate distance with high accuracy. Scientists used this method to map supernovae at extreme distances across the universe. And in 1998, the results came back wrong. Distant explosions were dimmer than expected. Not much dimmer, but enough. The universe was expanding faster than models predicted. The distant galaxies were accelerating away. Something was pushing space itself apart, growing stronger over time. Scientists named it dark energy. Nobody knows what it actually is. It makes up roughly 68% of the total energy content of the universe. And the only reason we know it exists is because a white dwarf crossed a mass limit somewhere in the distant universe and blew up at exactly the right brightness for us to use as a measuring stick. The Chandrasekhar limit, a number calculated by a 20-year-old on a boat, led directly to the discovery of the force reshaping the entire cosmos. But now scientists face a new question. If white dwarfs can pause their own aging by billions of years through the floating crystal mechanism discovered in 2024, then some of the supernovae we used as measuring sticks might have been older than we assumed, which means the measurements need checking. The universe may be even stranger than the dark energy discovery suggested. Before Type 1, a supernovae, measuring the universe, was guesswork wrapped in math. Astronomers had tools. Parallax, the slight shift in a star's apparent position as Earth moves around the Sun, works for nearby stars. Cepheid variable stars, which pulse at a rate tied to their brightness, stretch further, but beyond a certain distance, these methods lose precision. The universe is simply too big. Type 1, a supernovae, changed everything. Each explosion releases almost exactly the same peak energy, because each one is triggered by the same physical threshold. The Chandrasekhar limit does not vary. Quantum mechanics does not negotiate. So every time a white dwarf crosses that line and detonates, the flash has a known brightness. Astronomers call objects like this standard candles. A standard candle is any source of light where you know the actual output. If you know the true brightness and you measure how bright it appears in your telescope, the math gives you distance. The dimmer it looks relative to its known output, the farther away it is. Type 1, a supernovae, are the most powerful standard candles we have, bright enough to see across billions of light years, consistent enough that astronomers trust their measurements to within a small margin of error. Using these explosions, scientists mapped the expansion of the universe at distances never reached before. They expected to find the expansion slowing down over time. Gravity should pull galaxies together. Old, distant galaxies should be moving apart a little more slowly than younger, closer ones. Instead, the opposite appeared. Distant galaxies, seen as they were billions of years ago, were moving away more slowly than galaxies today. The expansion of the universe has been speeding up over time. Something is pushing space apart, and it is getting stronger. That something is dark energy. Now here is where the 2024 white dwarf discovery punches into this story. If floating crystals inside white dwarfs cause some of them to pause their aging by billions of years, then a white dwarf that looks young by its temperature might actually be ancient. A white dwarf thought to be 4 billion years old might really be 6 or 7 billion years old. The stars surrounding these white dwarfs, the clusters they belong to, have had their ages estimated partly using white dwarfs as clocks. If those clocks ran slow, the age estimates are wrong. And if star cluster ages are wrong, the distances we calculated from those clusters might carry small errors. Small errors in cosmic distance measurement compound over billions of light years. They shift the numbers on dark energy. They shift the estimate of how fast the universe is accelerating. This is not a crisis. The framework still holds. But it means astronomers are currently rechecking the age calculations of star clusters across the galaxy, using the new crystal model to correct the timeline. The measuring stick itself is being remeasured, and if the corrections are significant enough, our picture of the universe's expansion history may shift. Our understanding of dark energy may deepen, or reveal something entirely unexpected hiding in the math. A dead star with floating crystals inside it is rewriting the map of the cosmos. What those crystals actually are, and exactly how they form, is a story strange enough to pull you deeper. For half a century, the textbook story about white dwarfs was clean, Simple and completely wrong. Here is how that story went. A white dwarf forms. It has enormous residual heat from its violent past. With no fuel left, it starts radiating that heat into space. The interior cools steadily. As the temperature drops, the carbon and oxygen atoms inside slow down and eventually lock into a rigid crystalline structure. The star freezes from the inside out. Billions of years pass. The white dwarf goes from blazing hot to dim to cold to dark. Eventually, in theory, it becomes a black dwarf, a cold, invisible dead sphere floating in permanent darkness. That story was elegant, predictable. It gave astronomers a reliable clock because the cooling happened at a steady, calculable rate. Scientists could look at any white dwarf, measure its surface temperature, and estimate how long it had been cooling. From that estimate, they could determine the minimum age of the star cluster it belonged to. That method helped establish the ages of some of the oldest structures in the galaxy. The technique was called white dwarf cosmochronology, cosmos clock science, roughly translated. Astronomers trusted it, but there was a persistent problem. When scientists measured large populations of white dwarfs and compared their temperatures to the expected cooling curve, they found a strange pileup. Too many white dwarfs, sitting in a specific temperature range, more than the steady cooling model predicted. It was like looking at a traffic flow study and finding too many cars parked in one stretch of road. Something was slowing them down. Something was causing white dwarfs at a certain stage of cooling to linger longer than they should. The effect had been noticed for years. Theories were proposed. None fully explained it. Then, in 2024, astrophysicist Simon Bluin and his team published a new analysis of what happens inside white dwarfs during the crystallization phase. They modeled the exact chemistry of the freezing process and discovered something the old models had missed. The crystals forming inside white dwarfs are less dense than the liquid plasma around them. That single fact changed everything. In the old model, scientists assumed the crystals sank, denser core at the bottom, lighter material floating on top, freeze from the inside out. Simple and logical. But the chemistry does not work that way. The specific mixture of carbon and oxygen crystallizing at those pressures and temperatures produces solid material that is actually slightly lighter than the surrounding liquid. And lighter material in a denser liquid does exactly what ice cubes do in water. It rises. The crystals float upward. As they move, they displace the heavier liquid plasma, forcing it downward. That downward flow of heavy material releases gravitational energy. That energy becomes heat. The heat feeds back into the star. The cooling pauses. For billions of years, the white dwarfs sitting in that unexpected pile-up on the temperature chart were not anomalies. They were right on schedule. They had just been scheduled by physics that nobody had accounted for until now. Half a century of measurements, slightly off, and the fix came from the direction no one expected. The idea sounds like something from a fantasy story. Deep inside a dead star, tiny crystals form in a sea of glowing liquid plasma. They should sink. Everything heavy sinks, but these crystals do not. They rise through the liquid, slowly, steadily, like ice floating in a glass of water. And as they rise, they heat the star. This is the discovery that came out of 2024 research led by astrophysicist Simon Bluin. It is confirmed by direct modeling of the thermodynamics inside white dwarf interiors, tested against observed populations of real white dwarfs, and it matches the data that older models could not explain. Here is what is actually happening inside those stars right now. The interior of a white dwarf is not a uniform solid. As the star cools, the outer layers freeze into a rigid crystalline shell, but the deep interior remains a pressurized liquid plasma of carbon and oxygen atoms, kept in that liquid state by the immense heat and density of the environment. As temperatures slowly drop, the atoms in that liquid begin arranging themselves into solid crystal lattices. This is the freezing process the old models described. But what the old models got wrong was the density of those crystals compared to the liquid they formed in. The crystals turn out to be slightly enriched in oxygen relative to the surrounding liquid, and at the pressures found in white dwarf interiors, oxygen-enriched crystals are slightly less dense than the carbon-oxygen liquid around them. Even a tiny density difference matters enormously at this scale. The crystals pop free from wherever they form. They drift upward, slowly at first, then in a continuous process as more crystals keep forming throughout the liquid interior. A steady upward stream of crystalline material rises through the plasma, and at the same time, heavier liquid gets displaced downward. This exchange is called compositional convection. Heavy material sinking, light material rising. The same physical principle that drives the churning of Earth's mantle, the convection in a pot of soup, the movement of weather systems in the atmosphere. In a white dwarf, this convection is slow, invisible from the outside, but the energy it releases is significant. Every kilogram of heavy liquid falling toward the core releases gravitational potential energy. That energy goes directly into the thermal budget of the star. The heat generated by this continuous settling slows the overall cooling of the white dwarf dramatically. Scientists calculate that this mechanism can delay the cooling process by anywhere from 1 billion to a few billion years, depending on the specific mass and composition of the white dwarf. 1 billion years of extra warmth, pumped in by gravity and physics. No fuel, no fusion. Just crystals floating upward through a dead star. The white dwarfs affected by this process appear warmer than they should be for their true age. Before 2024, astronomers measuring their temperatures assumed the apparent warmth matched the actual age. Now they know better. Some of these stars are genuinely ancient, billions of years older than their surface temperature suggested. That changes the age estimates for entire regions of our galaxy, and it raises a question that no one has fully answered yet. We know this happens. We do not know exactly which white dwarfs experience it and which ones do not. A star dies, it starts cooling. Every model predicted a smooth, uninterrupted decline toward cold and darkness. Then the crystals begin rising and everything stops. Not forever, but long enough to rewrite timelines across the galaxy. Here is the mechanism in full. A white dwarf forms with an internal temperature of hundreds of thousands of degrees Fahrenheit. Over millions of years, it radiates heat into space. The interior cools at a certain temperature threshold, somewhere around 45 million degrees Fahrenheit. Inside the core, the carbon and oxygen atoms begin crystallizing. That is where the old model and reality split apart. In the old model, the dense crystals sank. The star continued cooling at a steady rate, and astronomers could calculate age from temperature with confidence. In reality, the crystals float, and that single difference triggers what scientists describe as a gravitational energy release mechanism. The lighter crystals rise, heavier plasma falls. Falling mass releases energy. That energy becomes heat. The star's interior temperature stabilizes, or even rises slightly before resuming its long decline. The pause can last anywhere from 1 billion to several billion years. During that window, the surface temperature of the white dwarf holds relatively steady. A scientist measuring the star during this phase would estimate a certain age based on temperature, but the star is actually far older. The crystal mechanism has been holding the temperature up, hiding the true timeline. Astronomers refer to this as a delay in the cooling sequence, and it shows up clearly in the data. When scientists survey large populations of white dwarfs and plot their temperatures on a graph, there is a visible crowd of stars sitting in the temperature range associated with this crystallization phase. Too many stars there, clustered together, piled up. The cooling delay forced them to linger in that zone far longer than the old timeline allowed. This pileup had been observed for years without a solid explanation. The floating crystal model explains it precisely. The match between the new model and the observed data is strong enough that the scientific community has broadly accepted it as the correct mechanism. But the consequences reach far beyond just understanding white dwarfs. Star clusters are groups of stars born at roughly the same time from the same cloud of gas. Astronomers use the white dwarfs in a cluster to estimate the cluster's age. The coolest white dwarf in the cluster gives the floor of the age estimate, since it has been cooling the longest. If those white dwarfs were actually older than their temperature suggested, the clusters are older than calculated. The ages of some of the oldest structures in our galaxy, the globular clusters that orbit the Milky Way like ancient satellites, may need to be revised upward. That revision changes our understanding of when the first stars formed, how quickly the galaxy assembled, how old the universe itself appears to be from the inside. A floating crystal in a dead star is quietly reordering cosmic history. And there is still something else happening inside these objects. Something violent. Something the crystals have nothing to do with. Something that involves planets being torn apart and their remains dissolved into the surface of the star. The dead star sits in space, cold by stellar standards, silent. Its fusion engine has been off for billions of years. Then something drifts too close. Maybe a rocky asteroid knocked out of its stable orbit by the gravitational shuffling that happens when a star dies. Maybe the remains of a planet that survived the red giant phase, its orbit slowly decaying over millions of years until it inches within reach. Whatever the object is, once it gets close enough, the white dwarf claims it. The tidal forces at work here are almost beyond imagining. Tidal forces arise because gravity weakens with distance. The side of any object closer to the white dwarf feels a stronger pull than the far side. For small objects, this difference is negligible. For an asteroid approaching a white dwarf, the difference becomes so extreme that the object gets pulled apart before it even makes contact. The closer side gets yanked harder. The far side gets yanked less. The object stretches, splits, breaks into pieces. Those pieces break again. Within a distance of roughly 1 solar radius from the white dwarf, called the tidal disruption radius, any rocky object larger than a few hundred meters will be torn completely apart. The debris forms a cloud that spreads into a flat disk orbiting the white dwarf. Astronomers have observed these disks. Infrared telescopes detect the warm glow of shredded rocky material orbiting at close range. The Spitzer Space Telescope and ground-based observatories have found these debris rings around dozens of white dwarfs. The material in those rings does not stay in orbit indefinitely. Friction from gas and radiation slowly causes the debris to lose energy and spiral inward. The rocky dust and rubble rains down onto the surface of the dead star, and then the white dwarf's own atmosphere becomes a crime scene. Remember how gravity pulls heavy elements instantly out of the white dwarf's atmosphere. Normally, all that remains is pure hydrogen or helium. So when astronomers detect silicon, calcium, magnesium or iron floating in the atmosphere of a white dwarf, they know something rocky was recently consumed. These heavy elements betray the chemistry of the destroyed object. The signature reads like a forensic report. Silicon and magnesium together suggest rocky material similar to Earth's mantle. Iron in certain ratios points to a differentiated body, one that had a metal core, like Earth or Mars. Carbon and oxygen ratios tell scientists whether the object was dry or once held water. Scientists have identified the chemical remains of planetary bodies in the atmospheres of roughly 25 to 30% of all observed white dwarfs. That means somewhere around a quarter of all white dwarfs have consumed rocky material from their former solar systems. This is not rare, this is normal. Dead stars routinely devour the remains of the worlds that once orbited them. And in 2015, the Kepler Space Telescope caught this process happening in real time. It observed the transit signature of a disintegrating rocky body passing repeatedly in front of a white dwarf, its orbit slowly decaying, a little more material shredding away with each pass. A planet dying in slow motion, captured as it happened. But what scientists found when they analyzed what these eaten worlds were made of led somewhere unexpected. It suggested that rocky planets around dead stars are surprisingly similar to the ones in our own solar system. which raises a question nobody has fully answered. Were any of those eaten planets once habitable? A white dwarf eats a planet. The debris rains down through its thin atmosphere. Gravity buries the heavy material almost immediately, but for a brief window, the chemistry of that destroyed world floats on the surface. And scientists can read it. The technique is called spectroscopy. When light passes through a gas, specific elements absorb specific wavelengths of that light. The result is a pattern of dark lines in the spectrum, a fingerprint unique to each element. By analyzing the light from a white dwarf's atmosphere, astronomers can identify exactly which elements are present and in what amounts. Finding calcium, magnesium, silicon, and iron in a white dwarf atmosphere is now routine. These are the same elements that make up the crust and mantle of rocky planets. Their presence confirms that the star recently consumed a rocky body. But scientists go further than simple detection. The ratios between elements tell a more detailed story. Rocky bodies in our solar system formed in different conditions and ended up with different chemical profiles. The inner planets are rich in rock-forming minerals. The outer regions have more ice and carbon. Objects that underwent core formation, where metals sank to the center while rock formed the shell, have a distinct iron-to-rock ratio. When scientists find iron-heavy signatures in a white dwarf atmosphere, they conclude the star ate something that had a metal core, something Earth-like, something that had time to differentiate into layers the way Earth did over hundreds of millions of years. This means these destroyed objects were not random chunks of rock. Some of them were fully developed geologically complex bodies. Some were old enough to have formed cores, mantles, and possibly crusts. Some may have had the right conditions for liquid water at some point in their histories. Scientists have detected the chemical signature of water-bearing minerals in at least a handful of white dwarf atmospheres. The evidence suggests that some of the consumed objects were water-rich, possibly once holding oceans or subsurface ice. If a planet can hold water, it can potentially hold life. And if a white dwarf is eating rocky, water-bearing worlds, then before those worlds were destroyed, they orbited a dying star in conditions that may have briefly supported habitability, not comfortable habitability. The death of the host star would have sterilized the inner planets, but outposts further out, or worlds that moved to warmer orbits during the red giant phase, could have had a temporary window. Temporary by human standards means millions of years. Researchers at institutions including Cambridge and UCLA have published studies on the chemistry of white dwarf pollution. They found that the bulk compositions of the consumed bodies closely resemble the rocky planets in our own solar system. The universe builds rocky worlds in the same way, repeatedly around all kinds of stars, and when those stars die, the white dwarfs left behind carry the dissolved chemistry of those worlds in their atmospheres for a few thousand years before gravity buries it forever. Every polluted white dwarf is a faint obituary for a world that no longer exists. What the crystals rising inside these stars are doing while all of this plays out on the surface, that story still has layers we have not uncovered yet. Most white dwarfs cool slowly, quietly, floating in space without drama. Some of them spin, and a few of them spin so fast that the entire dead star completes one full rotation in just a few minutes. For comparison, Earth takes 24 hours to rotate once. The Sun takes about 25 days. A white dwarf spinning in 2 or 3 minutes is rotating hundreds of thousands of times faster than our planet. The physics behind this comes from the same principle that makes a figure skater spin faster when she pulls her arms inward. When a large, extended object collapses into a smaller, denser object, it conserves its angular momentum. The spin stays roughly the same but is concentrated into a far smaller body. The rotational speed increases dramatically. A star that was slowly rotating before it collapsed can become a white dwarf spinning at extreme speeds. The original rotation is packed into a sphere the size of Earth. Now add a magnetic field. Many white dwarfs carry magnetic fields inherited and amplified from their progenitor stars. Some white dwarf magnetic fields are 1,000,000 times stronger than Earth's magnetic field. A few extreme cases are known to have fields 1,000,000,000 times stronger. A fast-spinning, strongly magnetized white dwarf becomes something different. It generates powerful beams of radiation that sweep through space with each rotation, like a lighthouse in the dark, but the light is radio waves, X-rays, or ultraviolet radiation, and the lighthouse completes a full sweep in minutes. Astronomers have detected and confirmed a class of these objects called highly magnetized or magnetic white dwarfs. Some are observed spinning with periods of just a few minutes. One system catalogued as AR Scorpii contains a white dwarf spinning fast enough to release pulses of radiation that can be detected from Earth. This system was initially mistaken for a type of variable star. When scientists looked more carefully, they found a white dwarf essentially blasting its companion star with radiation on every rotation. The companion glows and flickers in response to the pulses. The whole system throbs with the white dwarf spin. It was the first white dwarf ever observed behaving like a pulsar, the type of extreme spinning object usually associated with neutron stars. Faster spinning white dwarfs also have a relationship with the Type 1a supernova story. Some researchers propose that a highly spinning white dwarf can support more mass than the standard Chandrasekhar limit, because the spin adds outward centrifugal force to the quantum pressure. These so-called super Chandrasekhar white dwarfs might be able to accumulate extra mass before detonating, producing an explosion more powerful than a standard Type 1a. A few observed supernovae have released more energy than the standard limit should allow. Whether supermassive spinning white dwarfs explain those excess energy blasts is still an active area of research. The universe keeps finding new ways to break the rules we thought governed it. A white dwarf is born screaming with heat. When the core is first exposed after the red giant sheds its outer layers, the surface temperature can exceed 180,000 degrees Fahrenheit. For scale, the surface of our Sun sits at about 10,000 degrees Fahrenheit. The interior of our Sun reaches about 27 million degrees Fahrenheit at its core. A newly formed white dwarf is nearly 20 times hotter at its surface than the Sun. At that temperature, the radiation pouring off it is dominated by ultraviolet light and soft X-rays. The surrounding gas cloud, the planetary nebula left behind from the red giant phase, gets lit up by this intense radiation. The gas fluoresces in colors determined by its chemical composition. Oxygen glows green and blue, hydrogen glows pink, nitrogen produces red. These glowing shells, some of them spanning several light years across, are some of the most visually striking objects in the sky, and the energy source making them glow is the exposed core of a dead star. Over millions of years, the white dwarf cools, the ultraviolet output drops, the surrounding nebula fades as the gas disperses into interstellar space. The dead star becomes just a faint white point of light. Over billions of years, that point dims further. The surface temperature drops through 100,000 degrees, 80,000, 50,000. Eventually it reaches the range where visible light dominates, and the star appears white, pale blue, or yellow to instruments sensitive enough to detect it. The coolest white dwarfs we have found sit at around 7,200 degrees Fahrenheit. That is actually cooler than some types of stars, and it is in the range of an orange campfire. A dead stellar core, billions of years old, glowing dimly at campfire temperatures. These cool ancient white dwarfs are extraordinarily hard to find. They are dim. They have been cooling for so long that they have moved far from where they formed. Many of them drift as solitary objects through the galactic plane without any markers identifying their true age. Scientists call the coolest ones ultra-cool white dwarfs. Finding them is challenging even with modern telescopes. Their low surface brightness means only the closest ones are detectable. Thousands, possibly millions more sit beyond our current observational reach. Each cool white dwarf is a relic of a star system that completed its entire life cycle before our Sun even ignited. They predate our solar system. They predate the conditions that made Earth possible. Some of them formed when the Milky Way was young, and the universe looked completely different. And now we know that their surface temperatures have been lying to us. The crystal mechanism inside them has held their warmth artificially high for billions of years. The coolest ones we see now may have been paused at a higher temperature for so long that their true age dwarfs even our most generous estimates. The universe is older than it looks, and white dwarfs are part of the reason we did not realize it sooner. The next thing we need to explore is a concept so strange it has never actually been observed. Something colder than any white dwarf that currently exists. Something the universe is not yet old enough to produce. Not every white dwarf gets a pause button. The floating crystal mechanism that delays cooling by billions of years does not happen in all of them. It depends on the specific chemistry inside the star, the exact ratio of carbon to oxygen in the liquid plasma, the pressure at various depths, and the temperature at which crystallization begins. Change any one of those variables significantly and the crystals may not be buoyant at all. They might sink instead. And a sinking crystal releases no gravitational energy. The cooling continues on schedule. So which white dwarfs get the effect and which ones do not? That is a question scientists are still working out. The basic picture goes like this. When a star like our Sun dies and leaves a white dwarf behind, the core composition depends on how much fuel the original star burned and at what temperatures. More massive progenitor stars produce white dwarfs with different carbon to oxygen ratios than lighter ones. The exact mixture varies from star to star. The 2024 research showed that the buoyancy of the crystals depends sensitively on that mixture. A white dwarf with a core that is slightly more oxygen-rich will produce crystals that are lighter than the surrounding liquid. Those crystals float. The cooling pauses. A white dwarf with a different ratio might produce crystals that are denser than the liquid. Those sink. No pause. Steady cooling. The problem is that scientists cannot directly measure the interior composition of a white dwarf. The thin hydrogen or helium atmosphere completely hides what is happening inside. All astronomers have access to is the surface temperature, the mass, and occasionally the magnetic field or spin rate. From those external clues, they have to infer what is happening thousands of miles below the surface. This is like trying to determine the recipe of a dish by only smelling the kitchen through a closed door. Computer models help. Scientists run simulations of stellar evolution that track how much carbon and oxygen get produced during the helium burning phase of a star's life. Those models predict the interior composition of the resulting white dwarf. But the models themselves carry uncertainties because the nuclear reaction rates involved in helium burning are not known to perfect precision. A small uncertainty in the reaction rate produces a noticeable uncertainty in the carbon-to-oxygen ratio, and a noticeable uncertainty in that ratio is enough to change whether the crystals float or sink. So right now, the honest answer is this. Scientists believe that a significant fraction of white dwarfs experience the floating crystal delay. The observed pile-up of white dwarfs in the relevant temperature range suggests it is common, but the exact boundaries of which stars qualify and which do not remain an open problem. Resolving it requires either better stellar evolution models, more precise measurements of nuclear reaction rates in laboratories on Earth, or future telescopes capable of probing white dwarf interiors more directly. The answer matters enormously, because every white dwarf used as a cosmic clock has an error bar that depends on whether the floating crystal effect applies to it or not. Until that error bar shrinks, every age calculation built on white dwarfs carries a hidden uncertainty. And hidden uncertainty in the oldest, most fundamental measurements of the universe is exactly the kind of thing that, when corrected, changes what we think we know. Something even more fundamental waits in the next chapter. It involves the fate of the white dwarfs that never find a companion, never feed, never explode, and simply cool across timescales longer than anything that has ever been measured. In 2015, The Kepler Space Telescope was staring at a white dwarf located about 500 light-years from Earth. Kepler was designed to detect planets by measuring dips in starlight. When a planet passes in front of a star, it blocks a tiny fraction of the light. Kepler measured those dips with extraordinary precision across hundreds of thousands of stars simultaneously. What it detected around this particular white dwarf was not a clean, repeating dip from a stable planet. It was chaos. The light curve showed irregular, dramatic drops in brightness, multiple dips of different depths occurring at irregular intervals. Some blocks of starlight were partial, some were asymmetric, meaning the leading edge of the object blocked light differently than the trailing edge. The pattern matched one explanation. A rocky body was disintegrating as it orbited. Each time it passed in front of the star, a different amount of it remained. Debris trailed behind, in an irregular cloud. The object was losing mass on every orbit. A planet dying in real time, captured as it happened. Scientists estimated the object was somewhere between the size of a small asteroid and a dwarf planet. It orbited the white dwarf at a distance that put it well inside the tidal disruption zone, where the gravitational forces are strong enough to pull rocky objects apart. The orbit was decaying. Every pass brought the object slightly closer. The tidal forces got slightly stronger. More material shredded away. The debris cloud around the white dwarf grew. This single observation confirmed something that had only been inferred from atmospheric chemistry before. White dwarfs actively consume their planetary systems. The process is not ancient history recorded in atmospheric pollutants. It is ongoing, happening right now, around stars across the galaxy. Since that 2015 detection, astronomers using Kepler data and follow-up observations have identified additional transiting debris systems around other white dwarfs. Some show periodic signals consistent with intact but rapidly orbiting rocky fragments. Others show the same chaotic, irregular pattern of a body in the process of breaking apart. One system shows gas as well as dust in the orbiting debris, suggesting that volatile material is also being released as the rock heats and fragments near the stellar surface. The white dwarf is not just eating solid rock. It is processing a complex, layered object. What is striking about all of these systems is the orbital period. The debris orbits the white dwarf in hours. Some fragments complete a full orbit in under 2 hours. Objects the size of small mountains, circling a dead star, faster than the International Space Station circles Earth. At those speeds, the tidal forces are enormous. Any object without significant structural strength would be pulled apart immediately, and scientists watching these systems are essentially watching a planetary system erasing itself, one rocky body at a time. Over billions of years, the white dwarf methodically dismantles and consumes whatever remains of its former solar system. The detective work hidden in the chemistry of the atmosphere tells the same story. The atmospheric pollution observed in roughly a quarter of all white dwarfs suggests that this consumption is happening constantly. The Kepler observation just gave us a front-row seat for the first time. What comes next is not about destruction. It is about something that spins so fast and blazes so powerfully that it was mistaken for an entirely different kind of object. A white dwarf sits at the center of a binary system. Its companion star orbits close by. A red dwarf roughly 1/3 the mass of our Sun. Every 2 minutes, the white dwarf completes one full rotation. As it spins, its magnetic field, roughly 10 million times stronger than Earth's, sweeps through space like a searchlight. The radiation it produces, a combination of radio waves, optical light, and ultraviolet pulses, slams into the companion star on every pass. The companion star brightens, flickers, responds to the pulses like a lamp being switched on and off. This system, designated AR Scorpii, sits about 380 light-years from Earth. Scientists first noticed it behaving strangely in archival data. When they looked closely, they realized they were watching something that had never been seen before. A white dwarf behaving like a pulsar. Pulsars are rapidly spinning neutron stars. They are smaller, denser, and far more extreme than white dwarfs. But the mechanism producing the pulsing radiation is similar. A rotating magnetic field generates a sweeping beam. AR Scorpiae was the first white dwarf confirmed to operate by the same principle. It changed how scientists think about energy output from dead stars. The white dwarf in AR Scorpiae is losing rotational energy. It is spinning down slowly, transferring that energy into the radiation it blasts outward. The companion star absorbs some of that energy. Its atmosphere heats up. It glows more brightly on the side facing the white dwarf. The system pulses with a period of just under 2 minutes, regular enough to set a clock by, intense enough to detect with a moderate amateur telescope under the right conditions. But AR Scorpii is at the extreme end of a broader phenomenon. Magnetic white dwarfs as a class are common. Roughly 20 to 30% of all white dwarfs carry measurable magnetic fields. Most of these fields are far weaker than AR Scorpii's, but still far more powerful than anything in our ordinary experience. The strongest magnetic white dwarfs known carry fields roughly 1 billion times more powerful than Earth's magnetic field. Scientists call these ultra-high field magnetic white dwarfs. They are rare, but confirmed. A handful of them have been catalogued. At those field strengths, the physics of the atmosphere changes completely. Atoms do not behave normally in magnetic fields that strong. Electrons orbit the nucleus differently. The spectral lines used to identify elements shift and split in complex ways. Reading the atmospheric chemistry of an ultramagnetic white dwarf requires entirely different analytical tools than those used for ordinary white dwarfs. Magnetism may also affect the crystal formation process happening inside these stars. If the magnetic field is strong enough to influence the behavior of the liquid plasma interior, it could alter the rate at which crystals form, the direction they drift, or the efficiency of the buoyancy mechanism. Whether ultramagnetic white dwarfs experience the same cooling delay as ordinary ones is currently unknown. The interaction between extreme magnetism and interior crystallization has not been fully modeled. Add that to the list of open questions surrounding these objects. Every answer seems to reveal 2 more questions, and the next one involves something the universe has not yet produced, but will, given enough time. Everything about the floating crystal discovery points toward one critical unknown. Scientists do not yet know the precise carbon-to-oxygen ratio inside most white dwarfs. That ratio is the key variable. It determines whether the crystals that form during cooling will be lighter or heavier than the surrounding plasma. Lighter crystals float, release gravitational energy, delay cooling by billions of years. Heavier crystals sink, release nothing extra, and the star cools on the old schedule. The entire difference between a white dwarf that pauses its aging and one that does not comes down to a ratio of 2 elements in its core. And measuring that ratio from the outside is currently beyond our ability. Here is why the problem is so difficult. The composition of a white dwarf's interior is set during the helium-burning phase of its progenitor star's life. When the star runs out of hydrogen and starts burning helium, it produces carbon and oxygen in proportions governed by a specific nuclear reaction. That reaction is called the triple alpha process, where 3 helium nuclei fuse into carbon, and then some of that carbon fuses with an additional helium nucleus to become oxygen. The ratio of carbon to oxygen in the final white dwarf depends on how efficiently that second step proceeds. And that efficiency is governed by a quantity called the nuclear reaction cross-section, which describes how likely 2 particles are to fuse when they collide at a given energy. The cross-section for the carbon plus helium reaction has been measured in laboratory experiments, but the energies at which stars burn helium are extremely low, too low to measure directly with current equipment. Scientists have to extrapolate from measurements taken at higher energies down to the stellar burning range. That extrapolation carries uncertainty. The uncertainty is currently around 15 to 20%, depending on the measurement technique used. 15 to 20% uncertainty in a nuclear reaction rate translates into meaningful uncertainty in the carbon-to-oxygen ratio in the white dwarf. And meaningful uncertainty in that ratio means scientists cannot confidently predict which white dwarfs get the floating crystal effect and which do not. Labs around the world are working to narrow this uncertainty. Facilities designed specifically to measure nuclear reactions at very low energies have been built underground, shielded from cosmic ray interference that would otherwise swamp the faint signals being measured. The Lunar Laboratory in Italy, located deep beneath a mountain, is one of the leading facilities for these measurements. Physicists there work to pin down reaction rates at energies closer to the actual stellar burning range. Each improvement in precision feeds directly into better models of white dwarf interiors. Until those measurements improve, the floating crystal story has a gap at its center. The mechanism is confirmed, the consequences are established, but the exact map of which white dwarfs carry the effect and which do not remains incomplete. Every major answer in astrophysics seems to rest on something only a different field of physics can provide. 5 billion years from now, our Sun collapses into a white dwarf. It has spent its entire life burning hydrogen and helium into carbon and oxygen. The white dwarf it leaves behind will be made almost entirely of those two elements. The question that follows from the 2024 crystal discovery is direct and strange. Will our Sun's white dwarf float its own crystals? Will it pause its aging? The answer depends on the carbon-to-oxygen ratio inside the core our Sun produces, and that ratio is connected to the same nuclear reaction rate uncertainty scientists are currently trying to resolve in underground labs. Current best estimates suggest our Sun will leave behind a white dwarf with a core that is roughly half carbon and half oxygen, possibly slightly oxygen-rich depending on the model. That composition is close to the range where buoyant crystals form. It could fall on either side of the threshold. If the ratio is oxygen-rich enough, the crystals will be lighter than the plasma around them. They will float. The Sun's white dwarf will pause its cooling for potentially 1 billion or more years. It will glow warmer than its true age suggests, for longer than the Earth has currently existed. If the ratio falls on the other side, the crystals sink. The cooling proceeds on the old schedule. Right now, scientists genuinely do not know which outcome applies to our own Sun's future remnant. What they do know is that even without the crystal delay, the Sun's white dwarf will cool extraordinarily slowly. At current estimates, it will take hundreds of billions of years to drop below the temperature of the coldest known white dwarfs, trillions of years to approach true darkness. The universe is currently about 13.8 billion years old. A cooling curve stretching hundreds of billions of years means the Sun's white dwarf will still be faintly glowing long after the universe has aged 10 times its current age, long after the last active stars have burned out, long after the Milky Way has finished merging with its neighboring galaxies, long after the cosmic microwave background, the faint afterglow of the Big Bang, has stretched so thin it becomes effectively undetectable. The Sun's white dwarf will still be there, fading, but not gone, and somewhere in its deep interior, crystals will be forming, rising or sinking, either pausing the clock or letting it run. The universe will have a very long time to complete the experiment. But there is an endpoint to this story, a final state that no white dwarf has yet reached, and none ever will, at least not within any time frame the universe has yet produced. Every white dwarf is cooling, slowly, across incomprehensible stretches of time. At the end of that process, when the last of the heat has finally bled away into the permanent cold of deep space, what remains is called a black dwarf. A cold, dark, invisible sphere of carbon and oxygen. No light, no heat, no radiation of any kind detectable at a distance. A perfect ghost. The problem is that none exist. The universe is roughly 13.8 billion years old. The cooling timescale for a white dwarf to reach true darkness, cold enough to qualify as a black dwarf, is estimated at somewhere above 100 trillion years. Some models push the timescale to quadrillions of years, for the coolest and least massive white dwarfs. 100 trillion years. That is more than 7,000 times the current age of the universe. The universe simply has not had enough time to produce a single black dwarf. Every white dwarf that has ever formed, from the very first ones created in the early universe, is still warm, still glowing faintly, still radiating a trickle of heat into space. The coldest ones we have found sit at around 7,200 degrees Fahrenheit. By stellar standards, this is extremely cool. By black dwarf standards, it is practically blazing. To become a true black dwarf, a white dwarf would need to cool below the temperature of interstellar space itself, just a few degrees above absolute zero. That process takes so long that the stars currently being born today will have lived their entire lives and died before the oldest white dwarfs approach that temperature. This means something strange about our position in cosmic time. We exist in an era when the universe still has active stars, active galaxies, and white dwarfs that have not yet finished cooling. The universe is young enough that its full final state, a cold, dark collection of black dwarfs, neutron stars, and black holes sitting in expanding emptiness, has not arrived. We are watching the universe in its bright phase, the active, luminous, star-filled era that will eventually end. When it does end, the black dwarfs will be among the last things left, invisible, dense, cold spheres scattered across the expanding void, orbited by nothing, emitting nothing, floating in a universe too cold and too dark for life as we understand it to exist anywhere. Physicist Freeman Dyson and others have speculated about what the far future of the universe might look like during these eras. The timescales involved are so extreme that describing them meaningfully in human terms is almost impossible. But the black dwarf is the predicted endpoint for the vast majority of all stars that have ever existed or will ever exist, our Sun included. Most stars end as white dwarfs. Most white dwarfs will eventually cool into black dwarfs. In the very far future, they will be the most numerous type of stellar remnant in the universe. The universe will be full of them, and completely dark. Before that happens, something even stranger may occur inside those ancient cooling spheres. Something that takes place across timescales so extreme that even the black dwarfs themselves may not survive it unchanged. Not every white dwarf drifts alone. Some exist in binary systems where both stars died. Two white dwarfs orbiting each other in silence. No fusion. No light beyond their faint residual glow. Two dense spheres of carbon and oxygen, locked in a gravitational dance that has been going on for billions of years. These systems are called double white dwarf binaries. Astronomers have confirmed dozens of them. Models suggest they are actually quite common, perhaps comprising a significant fraction of all binary star systems in the galaxy. At first glance, two dead stars orbiting each other seems like the most inert thing imaginable. Nothing burning, nothing changing. Just orbital mechanics playing out forever. But nothing in the universe stays perfectly still forever. Binary systems lose energy over time through the emission of gravitational waves. Gravitational waves are ripples in the fabric of space-time, produced whenever massive objects accelerate in curved paths. The more massive and the closer together the two objects are, the stronger the gravitational wave emission. Two white dwarfs orbiting each other radiate gravitational waves continuously. The energy carried away by those waves comes from the orbital energy of the system. As orbital energy decreases, the two stars spiral inward toward each other. The orbit shrinks. The orbital period shortens. This process is extremely slow at large separations. A pair of white dwarfs orbiting each other at a distance of millions of miles might take billions of years to spiral together. But once the spiral begins, it accelerates. Closer orbits produce stronger gravitational waves, which carry away energy faster, which tightens the orbit further. The process feeds itself. At some point, the two white dwarfs are close enough that tidal forces between them become significant. Material from the lighter, less dense white dwarf can be pulled toward the heavier one. A slow transfer of mass begins between two objects that have been dead for billions of years. Then they make contact. The merger of two white dwarfs is one of the most energetic events possible in a stellar system that has no active star remaining. If the combined mass of the two white dwarfs exceeds the Chandrasekhar limit, the result is a Type 1a supernova. Two ancient stellar corpses, silent for eons, suddenly producing an explosion bright enough to be seen across the observable universe. If the combined mass falls below the limit, the merger produces a single more massive white dwarf, possibly with a different internal composition than either of its components, possibly with new conditions for crystal formation, possibly with a new pause in its cooling sequence that nobody expected. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was designed primarily to detect mergers of neutron stars and black holes. But future gravitational wave detectors, including a space-based detector called LISA, may be sensitive enough to detect the gravitational waves from double white dwarf systems long before they merge. This would give astronomers early warning, a preview of an explosion centuries or millennia before it happens. Two ghost stars, spiraling inward across deep time, sending advance notice of their destruction across the fabric of space. The spiral ends. Contact is made. Two dead stars merge. What happens in the next few seconds has only been modeled, never directly observed in real time, but the physics is understood well enough that scientists can describe it with confidence. The outcome depends entirely on the combined mass. If the total mass of both white dwarfs added together stays below the Chandrasekhar limit, the merger produces a single massive white dwarf. The collision is violent. The two objects do not simply stack neatly on top of each other. They collide at thousands of miles per second. The outer layers get thrown outward in a turbulent shell. The cores merge under immense heat and pressure. The resulting object is hotter than either of its components was before the collision. Its interior is thoroughly mixed, disrupting whatever crystal structures may have been forming inside each white dwarf individually. The new combined object begins its cooling process essentially fresh, from an elevated temperature, with an interior composition that is some blend of both progenitors. If that combined mass exceeds the Chandrasekhar limit, the outcome is completely different. The merged core has too much mass for electron degeneracy pressure to hold. The quantum pressure that has been holding each white dwarf stable for billions of years simply fails under the combined weight. The core collapses in under a second. Carbon fusion ignites across the entire core simultaneously. The star detonates. Type 1, a supernova. This is one of the two main pathways to these explosions. The other, which we covered earlier, involves a single white dwarf feeding from a living companion. The double merger pathway is sometimes called the double degenerate channel, and there is an ongoing debate in astrophysics about which channel produces more of the Type 1a supernovae we observe. Some observed Type 1 a supernovae release more energy than the standard Chandrasekhar limit predicts. This excess is hard to explain through the single white dwarf feeding channel, but two white dwarfs merging could in principle produce a combined mass that slightly exceeds the limit and generates a more energetic explosion. The data from observed supernovae shows a range of energies that the single feeding channel struggles to fully account for. The double merger channel fills in some of those gaps. But here is the part that carries the most consequence for everything we have discussed. Every Type 1a supernova used as a standard candle, every distance measurement built on the assumption of a consistent explosion energy, depends on the assumption that all these explosions come from the same physical setup. If some come from single white dwarfs crossing the Chandrasekhar limit from feeding, and others come from double mergers that slightly exceed it, the explosion energies are not perfectly identical. They are close, but close is not the same as identical. And in the universe, when your measuring stick varies even slightly, the measurements of the largest distances can shift enough to matter. The dark energy calculation, the expansion rate, the size and age of the universe, all of them built on the reliability of these explosions. The stars that died the most quietly, cooling alone for billions of years, are helping us measure the shape of everything. The oldest white dwarfs in the universe are nearly invisible. They formed early, when the galaxy was young and its first generation of stars burned fast and died. Those first white dwarfs have been cooling ever since, across timescales that dwarf the age of the solar system. Some of them have been cooling for 10 or 11 billion years. After that much time, they are dim, cool, faded to a glow so faint that only the nearest ones are within reach of our best telescopes. The coolest confirmed white dwarfs sit at surface temperatures around 7,200 degrees Fahrenheit. For reference, the surface of our Sun runs at about 10,000 degrees Fahrenheit, so the coolest dead stars are cooler than our living Sun. At those temperatures, the white dwarf emits mostly infrared radiation and red visible light. The surface glow is similar in color to a dim orange ember in a dying fire. Through a telescope sensitive to infrared, these objects appear as extremely faint red or orange points. Finding them requires searching for objects that are dim, small, and moving noticeably relative to the background stars. White dwarfs are dense and relatively nearby compared to the vast majority of stars. They drift across the sky at a measurable rate over years or decades, a motion called proper motion. Astronomers hunt for high proper motion objects and examine their colors and brightness. If the combination of factors matches a cool white dwarf signature, they flag it for detailed study. One of the most extreme examples, designated WD0346-011, sits just about 17 light-years from Earth, making it one of our closest stellar neighbors. Its surface temperature places it among the coldest known white dwarfs. It has been cooling for so long that scientists estimate it is among the oldest stellar remnants in our part of the galaxy. These ancient objects hold a specific scientific value. They represent the earliest white dwarfs the Milky Way produced. Their ages bracket the age of the galaxy itself. If the oldest white dwarfs can be confirmed to have been cooling for 11 billion years, the galaxy must be at least that old. But if the floating crystal delay affected these ancient white dwarfs during part of their cooling history, then their true age is even greater than the temperature suggests. These extreme cold relics might be older than any method currently estimates. The galaxy may be older than we think. The universe's star-forming history may have started earlier than models predict. Every cool, faint drifting point of light, hiding in the infrared, is a potential relic from a time the universe barely remembers, and at the extreme end of their cooling, something unexpected may still be waiting inside them. Right now, scientists can only observe white dwarf surfaces, the atmosphere, the temperature, the magnetic field, the spin rate. Everything happening inside, the crystals forming, the plasma churning, the compositional convection releasing heat, is invisible. But future telescopes may change that. The most promising tool is something called asteroseismology. The word means starquake science. When conditions inside a star change, the star can oscillate. It vibrates like a struck bell. Different internal structures produce different vibration modes. By analyzing the pattern of oscillations at the surface, scientists can infer what is happening deep inside. This technique already works for some types of pulsating white dwarfs. A class called ZZ Ceti stars pulsates with periods of a few minutes, producing measurable brightness variations. These oscillations probe the outer layers of the white dwarf to depths of a few hundred miles, giving scientists information about the crystallized shell and the partially liquid layer beneath it. But the crystal boundary, the transition zone between frozen solid and liquid plasma where the floating crystal action happens, sits deeper. Current asteroseismology methods reach it only roughly. The data is suggestive, but not definitive about what is happening at that depth. Next-generation space telescopes with extended observation baselines and higher photometric precision could detect fainter, longer-period oscillations that penetrate more deeply. The European Space Agency's planned Plato mission, designed primarily to find Earth-like planets, will also monitor stellar brightness with extreme precision over long periods. A byproduct of that precision Maybe asteroseismic data from white dwarfs good enough to probe near the crystal formation zone. Further in the future, dedicated white dwarf asteroseismology missions have been proposed. None are currently funded or approved, but the scientific case for them has been made in the literature. Gravitational wave detection offers a separate window. The LISA mission, a space-based gravitational wave detector currently in development by the European Space Agency, will be sensitive to gravitational waves at frequencies relevant to binary white dwarf systems. These waves carry information about the masses and orbital dynamics of the two objects. In principle, precise gravitational wave measurements from a binary white dwarf system could constrain interior structure in ways that electromagnetic observations cannot. LISA is expected to detect thousands of double white dwarf systems, creating a population large enough to study statistically. Patterns across that population could reveal signatures of the crystal mechanism. There is also the possibility of direct simulation. As computing power increases, full three-dimensional simulations of white dwarf interiors become more feasible. The crystal formation, the buoyancy-driven convection, the gravitational energy release, all of it could eventually be modeled in enough detail to make precise predictions about which stars experience the delay and by exactly how much. Science rarely delivers one definitive answer. It layers evidence, tool by tool, model by model, until the picture becomes clear enough to trust. The picture of what happens inside a dead star is becoming clearer, and the closer scientists look, the more they find that these objects are central to understanding the universe itself. Every atom in your body has a history. The hydrogen in the water that makes up most of your mass was forged in the first minutes after the Big Bang, nearly 14 billion years ago. The carbon in your DNA was cooked inside a red giant star that died before our sun was born. The oxygen you breathe right now was produced by massive stars that lived fast, burned bright, and ended in supernova explosions. But the iron in your blood has a specific origin story, and it leads directly back to white dwarfs. Iron is one of the most abundant elements in the human body and in the rocky planets of our solar system. It is the dominant element in Earth's core. It is the element that makes your blood red. Iron does not form easily in ordinary stellar burning. Stars like our Sun fuse hydrogen into helium, and helium into carbon and oxygen. Larger stars go further, burning carbon, oxygen and neon into silicon, and eventually into iron. But once a massive star has produced iron in its core, fusion stops. Iron does not release energy when fused, it absorbs it. An iron core is a dead end for stellar fusion. The star collapses. That collapse produces a core collapse supernova. These explosions scatter iron and other heavy elements into space, enriching the gas clouds that form the next generation of stars and planets. Some of the iron in your body came from this process, but a significant fraction of the universe's iron inventory comes from somewhere else. Type 1 supernovae, the white dwarf explosions, are extraordinarily efficient iron factories. When a white dwarf detonates, the runaway carbon fusion it undergoes produces a specific chain of reactions that creates enormous quantities of radioactive nickel. That nickel rapidly decays into cobalt and then into stable iron over the weeks and months following the explosion. A single Type 1 supernova can produce roughly 1 to 2 times the mass of our entire Sun in pure iron peak elements, most of which eventually becomes iron. This material gets blasted outward at tens of thousands of miles per second. It spreads across hundreds of light years. Over millions of years, it mixes with surrounding gas. That enriched gas eventually collapses into new star systems. Our solar system formed from gas that had already been enriched by multiple supernovae. Both the core collapse variety and the white dwarf variety contributed to the chemical mix that became our Sun, our planets, and eventually us. The iron in your hemoglobin was assembled in the detonation of a white dwarf. That white dwarf spent billions of years cooling. Crystals formed and floated upward inside it. It drifted through space after its host star died. Then, either by feeding from a companion or by merging with another dead star, it crossed the limit. And what it became helped build you. White dwarfs are not endpoints. They are contributors, active participants in the chemical evolution of the galaxy. Their explosions seed the next generation. Their cooling timescales influence the age of the universe as we measure it. They are quiet, but they are not irrelevant. Dark energy is the most abundant thing in the universe. It makes up roughly 68% of all the energy that exists. It is causing space itself to expand faster and faster over time, and nobody knows what it is. The only reason we know it exists at all is because of white dwarfs. Specifically because of Type 1, a supernovae. The explosions triggered by white dwarfs crossing the Chandrasekhar limit. In 1998, two independent research teams, one led by Saul Perlmutter and another led by Brian Schmidt and Adam Rees, were measuring the distances to Type 1a supernovae at extreme distances across the universe. They expected to find that the expansion of the universe was slowing down. Gravity should do that. The combined gravity of all matter in the universe pulling inward should gradually break the expansion left over from the Big Bang. Instead, distant supernovae were fainter than expected. Fainter means farther away. Farther away means the expansion of the universe was actually slower in the distant past than it is today. The universe was accelerating. Something is pushing space apart, something that grows stronger as the universe expands. Something that does not dilute the way matter and radiation do as space gets bigger. Physicists added it to the equations and named it dark energy. The discovery earned the Nobel Prize in Physics in 2011, but the measurement depends entirely on the Type 1a supernova standard candle being reliable, and that reliability now has new questions attached to it. If some Type 1a supernovae come from single white dwarfs feeding to the limit, and others come from double white dwarf mergers that slightly exceed the limit, the explosions are not all identical. The brightness varies slightly depending on the path taken. Using them all as if they were perfectly uniform introduces small systematic errors into the distance measurements. Astronomers are aware of this and have spent years studying Type 1a supernova light curves in detail, looking for subtle differences that might reveal the progenitor pathway. Progress has been made. Some supernovae show signs of hydrogen in their surrounding environment, suggesting the single feeding channel. Others show no such signs, suggesting the double merger channel. Correcting for this variation improves the distance measurements. Additionally, the 2024 discovery about white dwarf cooling delays means that white dwarfs used as age clocks in the same star clusters as observed supernovae may have been misdated. The age calibration of those clusters feeds into the calibration of the standard candle method. Every correction improves the precision of the dark energy measurement, and precision matters enormously here, because the exact value of the dark energy density determines the ultimate fate of the universe. If dark energy remains constant, the universe expands forever at an accelerating rate. Galaxies drift apart, stars burn out, white dwarfs cool into black dwarfs. The universe ends in cold, dark, permanent emptiness. If dark energy grows stronger over time, it may eventually tear apart galaxies, then solar systems, then planets, then atoms themselves. A scenario called the Big Rip. If dark energy weakens, gravity might eventually reverse the expansion. The universe collapses back inward. A big crunch. Which of these futures is real depends on measurements. Those measurements depend on white dwarfs. The dead stars at the end of an ordinary stellar life are the instruments we are using to determine the fate of everything. The first stars in the universe were nothing like our Sun. They formed roughly 100 to 200 million years after the Big Bang, in a universe that contained almost nothing except hydrogen and helium. No carbon, no oxygen, no iron, no rocky planets, just the two lightest elements, left over from the first minutes of cosmic history. Stars that form from pure hydrogen and helium behave differently from stars enriched with heavier elements. Without heavier elements to help radiate away heat during formation, the collapsing gas clouds needed to be more massive to trigger nuclear ignition. The first stars were enormous. Some may have been hundreds of times more massive than our Sun. Those giants burned intensely and died quickly. A star 100 times more massive than our Sun lives for perhaps a few million years before running out of fuel. It dies in a supernova so powerful it can leave behind a black hole directly with no white dwarf stage at all. But the range of first-generation stars was broad. Some were large and died violently. Others were smaller, maybe a few times the mass of our Sun, and lived longer. These smaller first stars did leave white dwarfs behind. Those white dwarfs are the oldest objects of their type in the universe. They have been cooling for roughly 13 billion years. They are the dimmest, coldest stellar remnants we could possibly detect, and they contain only carbon and oxygen, with no trace of heavier elements, because the universe did not have heavier elements yet when they formed. Finding one of these ancient relics would be extraordinary. Their chemical composition, pure carbon-oxygen with no contamination from later generation material, would confirm they predated the widespread enrichment of the galaxy with heavier elements. Their age would provide a direct measurement of when the first small stars finished their lives. The challenge is finding them. 13-billion-year-old white dwarfs are so cool that they emit almost no visible light. They are detectable only in infrared, and even then only if they are close enough. The nearest ancient white dwarf, if one exists within a few hundred light years, might be within reach of current or near-future infrared surveys. The James Webb Space Telescope, operating since 2022, has the infrared sensitivity to detect extremely cool, ancient white dwarfs at distances that earlier telescopes could not reach. Early results from targeted surveys are beginning to push the boundary of how old a confirmed white dwarf can be. Somewhere in the data streaming back from Webb's instruments, there may already be the faint signal of a star that died before our Sun was born, before Earth existed, before any rocky planet in the Milky Way had formed. A relic from the universe's first generation, still glowing, barely. Every star cluster in the Milky Way contains clues about when it formed, and one of the most powerful clues sits inside its white dwarfs. A star cluster is a group of stars born at roughly the same time from the same collapsing gas cloud. The most massive stars in the cluster burn fast and die first, leaving white dwarfs behind. The white dwarfs then cool steadily, or not so steadily, across billions of years. The coolest white dwarf in any cluster is the one that has been cooling the longest. Since all stars in the cluster formed at roughly the same time, the coolest white dwarf is the first one that died, the remnant of the most massive progenitor. Its cooling time tells you the minimum age of the cluster. This technique, called white dwarf cooling age dating, has been applied to dozens of clusters across the Milky Way and its satellite galaxies. It has produced some of the most precise age estimates we have for old stellar populations. But the 2024 floating crystal discovery introduced a new layer of complexity. If some white dwarfs in a cluster experienced a cooling delay of 1 to several billion years, then their apparent temperature is warmer than it should be for their true age. Using their current temperature to estimate how long they have been cooling gives a number that is too low. The cluster appears younger than it actually is. How much younger depends on how many white dwarfs in the cluster experienced the delay, and for how long each one was paused. Since this depends on the carbon-to-oxygen ratio of each white dwarf, and that ratio varies from star to star, the correction is not uniform. Astrophysicists are now developing updated models that incorporate the floating crystal effect into white dwarf cooling age calculations. The corrections for individual clusters range from hundreds of millions to potentially over a billion years, depending on the cluster's mass distribution and the fraction of its white dwarfs likely to experience the delay. Some of the oldest globular clusters, massive balls of ancient stars orbiting the Milky Way, have had their ages estimated at between 10 and 13 billion years using conventional methods. These clusters formed when the universe was young. They are among the oldest bound structures in existence. If white dwarf cooling ages in these clusters are revised upward by the crystal delay correction, the oldest globular clusters might turn out to be closer to the age of the universe itself than previously calculated. The gap between the age of the oldest structures and the age of the universe might shrink or disappear entirely. This has implications for cosmology. One of the ongoing tensions in modern astrophysics is the question of how fast the universe is expanding. Different measurement methods give slightly different answers, and this discrepancy is called the Hubble tension. If independent age estimates for old stellar populations shift upward, they add a new data point to a puzzle that has resisted solution for over a decade. A dead star's cooling curve is one thread in the largest tapestry in science. Here is a fact that should genuinely unsettle you. Everything we know about the age of the universe, 13.8 billion years, rests on multiple independent measurements: the cosmic microwave background, the expansion rate of space, the ages of the oldest stars. Each method has its own uncertainties, and those uncertainties are currently not fully consistent with each other. Some measurements suggest the universe is expanding faster than others indicate. The disagreement is called the Hubble tension, and it has not been resolved despite years of intensive study. White dwarfs sit at the intersection of several of these measurement chains. Type 1a supernovae, produced by white dwarfs, are one of the primary tools for measuring the expansion rate. White dwarf cooling ages contribute to the calibration of stellar population ages. The age of the oldest star clusters constrains the minimum age of the universe. If white dwarfs have been systematically misdated because the floating crystal delay was not accounted for, then multiple points in the measurement chain carry a quiet error. The error may be small, but in cosmology, small errors at key calibration points can shift the inferred age of the universe by hundreds of millions or even a billion years. The universe might be slightly older than 13.8 billion years, or the correction might be minor, well within existing uncertainties. And the picture holds as is. Scientists do not yet know which. The recalculation is ongoing. Researchers are systematically applying the new crystal delay models to every major white dwarf population used in age calibration studies. The results are being compared against independent measurements. What is already clear is that the universe is stranger and older looking than its most convenient description suggested. We thought white dwarfs were simple. They turned out to have floating crystals generating heat. We thought their cooling was a reliable clock. It turned out to be a clock that can pause for billions of years. We thought we had the age of the galaxy's oldest clusters nailed down. We now know those numbers need checking. Every time we have looked more closely at the universe's simplest objects, we have found something that forces us to revise what we thought we knew. That is not a weakness of science. It is exactly how it works. The universe does not simplify as we understand it better. It deepens. A dead star the size of Earth, sitting quietly in the dark, pumping out heat from crystals floating inside it, is helping us understand whether the universe is truly as old as we think. The last chapter of this story does not end with darkness. It ends with a question the universe itself is still answering. The universe has a future. Scientists can calculate it. Not perfectly, not without uncertainties. But the broad outlines are drawn by physics, and white dwarfs play a central role in what that future looks like. For the first few trillion years after today, stars will continue forming from gas clouds in galaxies. Massive stars will burn fast and die in supernovae. Medium stars like our Sun will swell into red giants, shed their outer layers, and leave white dwarfs behind. Small red dwarf stars will burn slowly, for tens or hundreds of billions of years, before they too fade. As time passes, the gas available for star formation gets used up. New stars form more slowly, Eventually, the raw material runs out, the last stars ignite and burn out over hundreds of billions of years. The era of active stars ends. What remains is a universe of stellar remnants. Neutron stars, black holes, and white dwarfs in enormous numbers. The vast majority of all stars that ever existed will have ended as white dwarfs. They are the most common stellar endpoint in the universe. In this long dark era, the white dwarfs continue cooling. Some are still being slowed by the floating crystal mechanism. Those pauses are temporary. Even a billion-year delay is nothing against the trillions of years left in the cooling curve. One by one, over incomprehensible spans of time, white dwarfs cool toward the black dwarf state. The first ones to reach true darkness will be the lightest and the oldest, those that have had the longest time to radiate their heat away. More massive white dwarfs cool more slowly in some respects and carry more total heat. A universe filled with cooling white dwarfs produces a faint, diffuse infrared glow across all of space. That glow dims as the centuries of trillions of years accumulate. Eventually, it fades below any conceivable threshold of detection. But even after the glow is gone, the black dwarfs do not simply sit unchanged forever. Proton decay, a predicted but never confirmed process suggested by certain theories of particle physics, would eventually dissolve the atomic nuclei inside a black dwarf over timescales of perhaps 1 to the power of 40 years. That is a number so large it makes the current age of the universe look like the first instant of a single second. If proton decay is real, the black dwarfs disintegrate. Matter itself unravels. What was once a star leaves behind only a diffuse haze of particles too light to form structure. If proton decay does not happen, the black dwarfs persist, dense, cold, dark spheres in an expanding universe. No light, no heat, no chemistry, no time that means anything by any biological standard. Our sun will become one of them. Everything that ever orbited it, every planet, every moon, every speck of dust from the inner solar system will have long since been consumed or rejected. The sun's black dwarf will drift alone through a universe too cold and too dark for anyone to see it. And yet, right now, in the era we actually live in, you can look up on a clear night and see white dwarfs. Faint points of light that are the exposed cores of dead stars. Inside each one, crystals may be floating upward through liquid plasma, pumping heat into a star that should have gone cold billions of years ago. The universe is quieter than it looks, and stranger than it sounds. The stars do not simply die, they linger. They surprise us. They build the iron in our blood, and the data in our telescopes, and the questions we cannot yet answer, and the dead ones are still talking.